We're going to see there's some cool things that happens when you transform exponential functions. And this lesson is all about understanding exponent rules. Now, do you understand exponent rules? Let's see. What's x squared times x cubed? Tell your neighbors, what's x squared times x cubed? Is x to the fifth or x to the sixth? What is it? So it's x times x times x times x times x. It's easy to kind of see that I'm multiplying x by itself 5 times. You get x to the fifth. However, what we are going to find is that it's not always just as easy as like adding 2 plus 3 and you get 5. Like what if I had a and b? What would you get if you multiply x to the a by x to the b? Tell your neighbors. Wrong. Yes. So what we see is that we're not like mushing the 2 and 3 together. If you said x to the ab, you'd be multiplying 2 and 3 together to get 6. You are taking the 2 and 3 and you're adding them together. So we need to be comfortable saying this. Okay? Why is it nice? I'll show you. Because what if it was 2 to the x plus 3? See that? It's almost like I'm starting with a sum in my exponent like I did x to the a plus b. Now this is something you've never done before because it's like, why would I do it? Exponent rules are usually used to simplify things. Well, I'm actually going to use an exponent rule to make this look different. It's not really simplifying it, but it's having me have a better understanding of maybe what 2 to the x plus 3 is equivalent to. We need to be comfortable going in this direction, but potentially in the other direction. If I say, what is 2 to the x plus 3 equal to, what would you tell me it's equal to? Tell your neighbors, what do you think 2 to the x plus 3 is equal to?
Or 2 to the x.
No, not plus. So, a number to the a times a number to the b is equivalent to the number to the a plus b, which means the number to the a plus b going in the other direction would be equal the number to the a times the number to the b. So 2 to the x times 2 cubed, which means 2 to the x plus 3 is actually equivalent to 8 times 2 to the x. Does this make sense? 2 to the x plus 3 is 2 to the x times 2 cubed. 2 cubed is 8. I'm just going to move the 8 in front. 8 times 2 to the x. Can you multiply the 8 and the 2 together and say this is 16 to the x? Tell your neighbors. Can you multiply the 8 and the 2 together? Say you get 16 to the x. Yes? No? No? Yes? No, definitely not. Okay? Think about it. If I plugged in 2 squared is 4. 4 times 8 is 32. If I plug in 2, 16 squared is not 32. So, importance. You're not allowed to take coefficients and multiply them by things being taken to powers. So, order of operations, exponents come first, then multiplication. This is it. Cool. What we will realize is that this is a horizontal shift. This is a vertical dilation. We had it on our quiz today. We will find with exponent functions that there are equivalences of horizontal shifts and vertical dilations. And let me show you an example. Let's take 2 to the x. I'm going to do the one that's very similar to what we just did first, the one on the right. I'm going to have f of x minus 4. Now tell your neighbors, what is f of x minus 4? And what's the transformation if you have f of x minus 4 from f to h?
It's 4 to the right.
Good. You're right. Do I have your phone, Woods, or is it on yourself for now? Let me see. Go find it. Yeah, just go ahead and put it on my desk there, bud. Yeah, great. Okay, so we got 2 to the x. And then we got 2 to the x minus 4. And boom, you guys see, we take our points like 0, 1. We shift it to the right, 4. We see the point 4, 1. Cool? We take the point 1, 2. We shift it to the right. We'll have the point 5, 2. We take the point 2, 4. We shift it to the right. We got the point 6, 4. Great. All right, cool. So we're comfortable with that h of x is 2 to the x minus 4, and that this should be right 4. And the formula is 2 to the x minus 4. But watch this, using exponent properties. Rewrite 2 to the x minus 4. Using the exponent property that we don't really use often, which is like a number to the a plus b equals a number to the a times a number to the b. 2 to the x minus 4 can be written as what?
Sorry. I know the answer.
What is the right answer?
2x times 2.
Good. We can rewrite this. I hope we're paying attention.
Yeah.
The 2 to the x times 2 to the negative 4. Now, 2 to the negative 4, we know how to figure out what that is. It's the same as dividing by 2 4 times. It's the same as a half to the 4th. It's the same as 1/16. All of a sudden, we get 2 to the x times 1/16, or I'm probably going to rewrite it a little bit differently so that I have 1/16 times 2 to the x. What did I just discover using this exponent rule? Tell your neighbors, what did I just discover using my exponent rule? That 2 to the x shifted to the right 4 is equivalent to 2 to the x vertically dilated by a factor of 1/16. That's a 16 and you know it. You take 2 to the x and you vertically dilate it by a factor of 1/16. And look, guys, it's on the same graph as 2 to the x minus 4. They are equivalent to each other, which means this shift right that you saw actually could be thought of as a vertical dilation. Take your y's, multiply them by 1/16. 1 turns into 1/16. 2 turns into 1/8. 4 turns into a 4th. And it's a pretty cool thing going on there, where it's like 2 transformations for 1. Okay, so a shift right is equivalent to a vertical dilation of 1/16, but only for 2 to the x. If I had any other different value, like 3 to the x or 4 to the x, we would have a different equivalent transformation. So do the one on the left for me. Tell me, a vertical dilation is equivalent to what kind of horizontal translation? This one's trickier. See if anybody can figure this out. So the formula for G is 8 times 2 to the x. Cool? Watch this. I'm going to rewrite 8 as 2 cubed. Now that I've rewritten 8 times 2 cubed, I have 2 cubed times 2 to the x. I can use my exponent property to combine. What do I get if you multiply 2 to 3 times 2 to the x? 2 to the x plus 3, which means plus 3. Plus. Yeah, that was a minus, so I had a minus. This is plus a negative. Okay, that's a negative. So 8 times 2 to the x equals 2 to the x plus 3, which means a vertical dilation of 8 is equivalent to a horizontal shift left 3 for 2 to the x. And this is just kind of us understanding and using exponent properties. So we know like multiple ways to handle things. Exponent properties are very important in mathematics to simplify things. And it's a cool thing that can show equivalent transformation. Not always will we just like ask you what is the transformation. We'll just sometimes say like, hey, 9 times 3 to the x can be written as 3 to the x plus k. What's k? Like 6. Yeah. Because we have to learn about logarithms. Into a 2-day and then a 4-day? No. Nah. It all fits. It all fits. It's K2. Yes, K2. 9 is 3 squared. 3 squared times 3 to the x, I would write as 3 to the 2 plus x, which is the same as 3 to the x plus 2. I'm telling you right now, there's a lot of you here that are like, oh, yeah, this is easy. This is a piece of cake. There are a lot of you here that have yet to actually do any of the examples that I've asked you to do. Okay, so maybe this is the one that you're going to do. 2 to the x minus 3 can be written as k times 2 to the x. What's k? If you haven't done one yet, now's the time to try. Is it? Yeah, exponent rules are tricky, especially these where we're doing things in like random order. Here's the key. X to the a times x to the b is x to the a plus b. I don't like using x though. We'll say a number to the a times a number to the b is a number to the a plus b. This rule goes in both directions. If we have a sum, we can split it into a product. If it's a product, we can split it into a sum of the exponents. Good. We start by saying 2 to the x times 2 to the negative third. You could say k is 2 to the negative third, but I'd like you to probably simplify that. So what's 2 to the negative third? Boom. You have K. K is 1/8. Cool. Now, what could we have just done is the following. Let's say for the top one. After doing what we're just doing, 3 to the x. Please look at the equation y equals 3 to the x. Tell me, what are two equivalent transformations of 3 to the x based on the work you just did? Tell your neighbors. Make sure you're picking up what I'm putting down. What are two equivalent transformations of 3 to the x based on the work that you've just done? Ready? A vertical dilation of 9 is equivalent to a horizontal shift left 2. Sorry. Yeah, no, that's it. A vertical dilation of 9 is equivalent to a horizontal shift of 2 to the left. Elander, if you take 3 to the x and multiply it by 9, what would you say that transformation is? If I put a 9 in front of 3 to the x, what do you think that transformation is? No. It's a vertical dilation of a factor 9. Cool. What would you say if I said 3 to the x plus 2? What type of transformation is that? 2 to the left. That's it. A vertical dilation of 9 is equivalent to a horizontal translation of 2. You want to see it? I'll show it to you. 3 to the x. 3 to the x plus 2. Is it plus 2? That is plus 2. And 9 times 3 to the x. 9 times 3 to the x and 3 to the x plus 2 are on top of each other. Okay. Look at maybe this point 1, 3. Shift it to the left 2. Okay, I have the point 1, 3. Negative 1, 3. There it is. Take the y coordinate, multiply it by 9. I should have a point 127. Boom. We get the same graph 2 different ways. All right, let's go to the bottom here. F of x divided by 16. Describe two equivalent transformations of taking f of x and dividing it by 16. I'll help you to start. I'd probably start by saying dividing by 16 is the same as multiplying by 1/16. That is one type of transformation. You can write down what that transformation is. But now, tell me an equivalent transformation. So, we're starting with 4 to the x, not 2 to the x. Got it. Now you have to be able to describe what you just said, what you're showing me. Too much. 4 to the 4th is not 16. Good Caballero. Don't write it like that though, but like, and it's not right either. No.
No?
You're right. That's not right. What's 4 to the 4th? No, that's not right. That's right.
I got you.
Check with Alan. Check with Rati. We got this, Ross? What's going on? Okay, but just like show me the equivalent equation. Just keep going. Keep going. Yes, you got it now.
There you go, sir. What if I told you?
No. Why not? Why do you have 2? It's a 4. Let's stay with 4. 16 is what? In terms of 4.
Better, I think.
No, it's not. 16 is 4 squared, right? So 1/16 is 4 to the negative second, right? Okay. So, ready? Here's what I'm doing. I'm paying attention, and this is kind of like something that we're just going to get used to the base. The base is 4. Okay, I'm going to try to keep everything in terms of 4 to a power, unless something else happens, which we'll see in the next page. I know 4 squared is 16. That means 4 to the negative second is 1/16. So I'm going to rewrite G as 4 to the negative second times 4 to the x, which means this can be written as 4 to the x minus 2, which means a vertical dilation of a factor of 1/16 is equivalent to a horizontal translation of 2 to the right. Got it? Cool. Now, there are other properties we have to worry about, like the following. What's x squared cubed? So, what is x to the a to the b? What's x to the a to the b? X to the a times b. What we are going to have are numbers to the a times b, which means sometimes we'll be able to do a number to the a, get that out of the way, and then do it to the b. For example, 3 to the negative 2x is equivalent to 1/9 to the x. Do you know why?
Yes, I do.
Why?
Because if you do 3 to the negative, dude.
You can rewrite this as 3 to the negative 2. Do that first, and then take it to the x power. 3 to the negative second is the same as 1/3 squared. So using exponent properties will allow you to maybe simplify numerically the base. All of a sudden, we can change our base based on what's going on in terms of like a product of our exponent. We like to stay away from horizontal dilation. Okay, but here's an example of some horizontal change in terms of like a dilation. If we put a negative in front of x inside the function, this is a horizontal reflection. Okay, this is new to you, but it's not new to you if you took algebra 2. That means 4 to the x, which looks like this, starts at 0, 1, increases by 4, exponential growth. If I sketch g of x being 4 to the negative x, everything's going to reflect over the y-axis. Looks like that. Okay, so this point popped over there. That point popped over there. So all of a sudden, it reflects over the y-axis. Does this make sense in terms of a reflection over the y-axis? Well, tell me, what type of exponential function is this that you're used to, and what type of exponential function is this that you're used to? Tell your neighbors. Yeah, so it looks like the graph on the right is a decay. Well, watch. 4 to the negative x can be written as 4 to the negative 1 times x. Everybody write this down. Which can be written as 4 to the negative first to the x, which can be written as 1/4 to the x. Reflecting over the y-axis is equivalent to changing your function from a growth function to a decay function. Cool? Now, we won't specify horizontal dilations, translations, but we will test that you understand this property. It started as a growth. It was 4 to the x. Times 4, times 4, times 4, times 4. No, then that changed to, this was the graph of 4 to the x. I reflected it over the y-axis. It became this graph, which is a decay graph. Yeah. Into? No. Okay, cool. All right. Ready? Here's what I would do here. 25 times 90 to the x is the same as 25 times 3 to the ax. What's a? Well, sometimes you need to be comfortable saying, oh, 9 to the x needs to be written as 3 to the ax. I'm going to change 9 into 3 squared. So I'm going to write this as 25 times, 9 to the x turns into 3 squared to the x. A power to a power, we multiply our powers. 3 to the 2x. A's got to be 2. This is showing that I understand this other property of a power to a power within the context of an exponential function. If you take 25 times 9 to the x, could you rewrite it as 25 times 81 to the bx? What would b have to be? No. No. Yep.
Wait, what?
To what? Ready?
I'm confused.
81 to the 1/2 is the same as 9. No, they're not. What is 4 to the negative second power? What is 4 to the 1/2 power? Okay, they're not the same. So, what we realize is 81 to the 1/2 power is 9. I replaced 9 with 81 to the 1/2 because I want this 81 here. So I have 81 to the 1/2 replacing 9 to the x. Well, that can be written as 25 times 81 to the 1/2 times x. A power to a power, you multiply the power. B has to be a half.
Yeah.
Okay. Introducing you to something that you probably investigated a little more further, and it's actually not important to really understand where it comes from. The value E is called a natural constant. E which is 2.7182854 something something, is actually equivalent to, and pops up a lot when you're using infinity. This number occurs naturally in mathematics. I'll show you the number again. E is 2.71828182846, and then it changes. Watch if I take 1 plus 1 over a number to the number. I'm going to plug in 987654321, and you will see 987654321 that this number 2.71828, as I make this number bigger, we will get closer and closer to E's equivalency. All you guys got to know, it shows up naturally in mathematics similar to pi. Just shows up and is used in a lot of different formulas in like physics, in the real world, because it just shows up naturally. You know where pi comes from, Linder?
The bakery.
It comes from a circle, yes. What specific parts of the circle does pi come from? No, but yes. It's the circumference divided by the diameter. The circumference is the perimeter of the circle. Take the perimeter of a circle, measure it, divide it by the diameter, you get pi. Cool? Naturally occurs. Now, you guys have to know e to the x is just an exponential function. We're multiplying by e over and over and over again. If I say, hey, what's e to the x plus 2? You should know that it's the same as e to the x times e squared. You could be like, oh, shifting e to the left 2 is equivalent to vertically dilating e to the x by a factor of e squared. If I say e to the negative x, you'd be like, oh, okay, that's the same as e to the negative 1 to the x, which is 1 over e to the x. It's just nothing crazy. It's almost like it's its own little variable, only it's not a variable, it's a number. Is y equals e to the x a growth or decay function? Why? Because e is bigger than 1. Take any number, multiply it by e over and over and over again. You're essentially tripling it. You're like 2 3/4 sizing it every time. Okay? Okay. Now, we're going to go to the homework instead of me giving you extra examples because I want to get to some problems right here that I really enjoy. I enjoy doing them. I think they're good problems. And it shows you understand the exponent rules and how they can go in multiple directions.
Let's give Grant. I think
Okay. Now, we're going to keep words out of these. We're going to keep words out of these. All we're going to try to do is use exponent rules to rewrite what we're given as one number times another number to just the x. You need to figure out what this number is here and what this number is here. I'll tell you the answer to the first one. It's 16 times 16 to the x. So the first number is 16, the second number is 16. How did I get 16 times 16 to the x? The answer is 16 times 16 to the x. How do you get that? That's it. We use the product property rule. We need to maybe put down somewhere on our homework that if we have a number to the a, b, it's equivalent to the number to the a to the b. 4 to the 2x. Since it's 2 times x, I would write this as 4 squared to the x. 4 squared is 16. That's how I get 16. That first number did not change. All that changed is the base went from a 4 to a 16. So, boom, the answer to the first one. Second one, the answer is 2 times 4 to the x. Can you get that? It's not that, Rock. It's not that, Linder. It's not 32 times 1/16 to the x.
Oh, I got it.
The answer I just told you is 2 times 4 to the x.
I know, but I got why.
Okay, good.
Before you should.
Good. There you go. No, it's not. It's 2 times 4 to the x. I'm telling you what the answer is, guys. This is the answer. That's the answer. You got to figure out how to get that. I'm not giving you the answer all the time, though. Maybe you need to write down that a number to the a plus b is the same as the number to the a times the number to the b. This is your other exponent rule. And I know, guys, I know right now, sure, I know right now that some of you are over all of the problems that we've done. Maybe you've gotten 1 or 2 right. These exponent rules are tricky. You will need to practice.
Okay, so, no, here I got...
Yeah, but that's not what I want. Yes, you're doing good stuff, but I just want a number and the number to the x.
I got x 2, but it's not 2 minus 1 because this is x.
Yeah, I just want x. I am going to write this as 32 times 4 to the x times 4 to the negative second. I'm going to leave the 4 to the x because I can't multiply anything by 4 to the x. I'm going to multiply 32 and 4 to the negative second together. 4 to the negative second is 1 over 16. 32 times 1 over 16 is 32 divided by 16. That's how I get 2. See if you can get the next one. If you have been missing up on all of them, it's okay. These are tricky, but you have to try. What's going to happen is some of you are going to go home, feel like this class is easy, even though you failed the last time. You are going to copy down the homework video. You'll be like, this is fine. I'll figure it out during class. You're not going to be able to figure it out. Exponent rules demand practice. You tell me what the answer is. Yes, it is 8 times 4 to the x. Algebra 2 is not 10 times harder. Oh, we have homework videos, which are where your answers are. If you ever have questions, you have a homework video. You don't have to watch it. Okay. All right. I feel good about myself. Everything's going well. And then I get to this one. What do we get? get the right answer.
No. Mathematics.
What are you talking about?
Would it be better to just add this
Oh, yeah. All right, I would write this as 8 times 3 to the x plus x. That's 3 to the 2x. Oh, I would write this 3 to the 2x is 3 squared to the x. If you haven't gotten any of these yet, try the next one. Like this one. Let's do this one on the right. I want to get to the bottom middle one because that's my favorite.
Bottom middle. Oh, that one looks like a little special guy, doesn't it?
Okay, do the one on the right. 10 times 5 to the x times 5 to the x minus 1. Write it as a times b to the x. Show me you understand exponent rule. No, I'd have to do more.
Is it 10 multiplied by 5 to x minus 1?
Sure, keep going. I want just x, 5 to the x. I just want one x.
Is this right? No,
The one in the middle is 2 times a half to the x.
No?
No, but that's the key is like, we might have right forms, but we want a very specific form for our answer. Okay, this is 10 times 5 to the 2x minus 1. I'm adding x and minus 1 together. There are other ways to do this, but I'm going to do it this way. This is 5 to the 2x times 5 to the negative first. This is 5 squared to the x. This is 1 over 5. 10 times 1/5 is 2. I get 2 times 25 to the x. Look at the bottom middle one. Now, guys, I do the problems on the homework video, and I'm like, you know what? I love doing these because I've done a lot of them, and they're like fun little puzzles. You guys haven't done a lot of them, okay? If you feel like you're just going to figure it out, you're going to bomb the next one, okay? You have to practice these. I saw this, and I'm like, oh, you should probably rewrite this as 4 to the 1/2 times x plus 3. Dividing by 2 is the same as multiplying by 1/2. And that means I could write this as 4 to the 1/2 to the x plus 3, which is 2 to the x plus 3. If you're just copying this down, not really helping you. This is 8 times 2 to the x. Yep. Practice. Do your homework, okay? No, I'm not. 2 cubed.
Huh?
2 cubed.
Wait, what did you say that was right?
8 times 2 to the x.